This video accompanies our paper Real-Time Online Learning for Model Predictive Control using a Spatio-Temporal Gaussian process approximation. It gives a high-level introduction to our approach on learning unknown system dynamics online in closed-loop control and presents experimental results from an exemplary application in miniature autonomous racing. Let's start by considering a nonlinear MPC formulation where we are especially interested in the model of the system dynamics. That's because these are disturbed by an unknown perturbation which is not captured by our nominal model. These residual dynamics may depend on system state and control input, but can crucially also be time varying. In our pursuit to improve MPC control performance, the goal is to learn the residual dynamics from data. Therefore, they are commonly modeled as a Gaussian process. This offers a flexible approach in learning a wide range of disturbances and allows to make uncertainty-aware predictions of the future state trajectory. However, it computationally scales poorly with training dataset size, and lifelong online learning without discarding data thus becomes impossible. In order to address this limitation, we choose a GP kernel that is separable into a spatial and temporal component. We then apply an inducing point approximation to the spatial kernel and represent the temporal covariance as a Markov transition model. What results is an approximate spatio-temporal GP model that enables indefinite online learning from a continuous stream of data at constant computational cost by using the Kalman filtering algorithm. A detailed formal description of this procedure, as well as the integration into an MPC formulation, can be found in our paper. We start our hardware experiments by looking at a model predictive controller based on the nominal system dynamics only. Its aim is to autonomously race a miniature car around the track. Initially, it performs this task reasonably well. After some time, we start adding a time-varying disturbance on the car steering. As a result, the controller becomes unable to drive consistent and good racing lines. This also shows in slower lap times, indicating a significant decrease in control performance. Now let the controller employ an approximate spatio-temporal model of the residual dynamics. This provides uncertainty estimates of the car's predicted state trajectory. Again, we induce the same time-varying perturbation on the car steering. The GP model is able to learn from streaming data, which allows the controller to adapt its behavior to the disturbance. As a result, control performance remains largely unaffected by the perturbation. While a naive GP implementation would not be able to keep this continuous learning up for an extended period of time due to the quickly rising computational cost, the proposed spatio-temporal approximation performs this task at a constant sampling time. Therefore, this GP-MPC controller can run indefinitely with online learning while remaining real-time capable. Our experimental results showed that the proposed approximate spatio-temporal GP-MPC strategy can offer improved control performance under a time-varying perturbation. In contrast to standard GP-MPC methods, it can achieve lifelong online learning from streaming data in real time without discarding any data points. The published source code and all experimental data can be found by following the links or the QR code on screen.